Okay, I'm here to show you about this classifying rational and irrational numbers. So I think that a really good thing to do first is to set this aside and show you what rational and irrational numbers are. So we have, well, to begin with, we have real numbers. Yes, and there are such thing as imaginary numbers, but that's not the topic of this. I'm talking about real numbers, and within real numbers, there are rational and there are irrational numbers. Now, our irrational numbers would be something like pi, something like the square root of 5, and so on. And I'll explain that in more detail. But rational, the official, the semi-official explanation or definition of it is it's a fraction. It's a fraction made of integers. So you might be wondering, well, wait, what's an integer? Those are the positive and negative whole numbers, including 0. So if I have a fraction, such as, I don't know, like, and I make it of integers. So one integer would be, how about 2? That's an integer. And 3 is an integer. And there's a rational number, 2/3. Negative 4 is an integer. And 5 is an integer. So together you have a rational number because it's a fraction made of integers. Integer, 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 integer. Um, and so what we would have is we can turn all of these into decimals. And the decimal is what really helps help you visualize what these rational numbers are. If you were to plug this into a calculator, you would get 0.66666 and so on. And to me, rational means it's like a rational person. You know what they're going to do. They're predictable. And so this is very predictable. You know that the next number is going to be a 6 forever. There's this repeated pattern. And that pattern is that it's 6 forever. Or a rational could be something like -4/5, where that is, if you plug this into a calculator, 4/5 is 0.8 and it is negative. So this would be terminating. This comes to an end and this is repeating. So rational numbers end up with decimals that are either repeating or they are terminating, which means they come to an end. Now, the irrational numbers, they end up with decimals that are not repeating and they are not terminating either. So this pi is a pretty famous one where that is 3.14159 and so on. There are no patterns to this. No number repeats, no patterns, no amount of numbers repeat or anything, and it never ends. So it's non-terminating and it's non-repeating. And the square root of 5 is a similar thing where I'm pulling up my calculator right now because I don't remember what the square root of 5 is. It is, let's see, it is 2.236. It's about, so I should be writing the about symbol, 2.236. It's not precisely that. Maybe I'll just, so nobody gets upset with me, I will say this is about, those squiggly lines mean it's about. It's not exactly that, but it's about that. And this keeps on going, but it doesn't repeat. So those are irrational numbers. Now, I could also have something like this on the rational side. I could have the square root of 9. And that's asking what times itself is 9. Well, 3. 3 times itself is 9. And so that's rational. So it doesn't have to be a decimal, although it could be a decimal. We could call this a terminating decimal. It's 3.0. Or we could express this as a fraction made of integers, and that would be 3/1. See, there's multiple ways of showing this, but it's still rational. But the square root of 5, that is irrational. So what we could do is I could do this. I'm going to bring this over and I'm going to do this. So the square root of 1, and I'm going to separate this here. So when we're talking about square roots, the square root of 1 is 1. The square root of 2, putting in a different color for a reason, is 1.14. I don't know what that is after that. The square root of 3, I have no idea. I'll do that here. 3 square root, 1.732, 1.732, and so on. But the square root of 4, I know, is 2. Square root of 5, I said that earlier, it's 2.236. And when I say equals, I mean about 36. The square root of 6, don't know what that is. That's 6 and square root 2.449. 2.449. The square root of 7, nope. I'm getting to a point here. I'll stop at 9. 2.645. Square root of 8, don't know what that is. I mean, that's saying what times itself is 8. 2.828. And I'll do this. Square root of 9 is 3. So I'm hoping you notice here what I was doing. I was noting these that I call nice square roots. All the ones with nice square roots, they are rational. So the stars are rational. And the rest are irrational. So there's a bunch of square roots that are rational, and they're called the perfect squares. So the square root of 16 is 4, and the square root of 25 is 5, and so on. But all the square roots in between, like the square root of 10, square root of 11, and square root of 12, those were all irrational. So now that you have a basic understanding here, hopefully, let's get back to our problem. Okay, so we have this, is it rational? Oh, well, this is definitely rational, and I'm going to blow this up a little bit more here. And yeah, this is definitely rational for 2 reasons. 1, it's repeating, and 2, it comes to an end. So I'm picking rational for sure. Checking that bad boy. Okay, let's look at more. So is it rational or not? Well, this includes pi. And as I was showing you here, pi is irrational, and anything multiplied by pi is going to be irrational as well. So that is irrational. This one, so this is a repeating decimal, and that's okay. This is a good one to show actually, because if I have 0.151 with a bar over it, that means I have 0.151, so that 151 gets repeated forever. And this is a repeated pattern. That could be rational. Because there's something else I should show you about this. Let's step over to my office over here. Let me bring this out. You know what? Actually, I want to keep that there. I'm going to bring this all over here, and let me show you something else. It's a little, this is actually one of my favorite things. I absolutely love this. So let's say if I have 0.11111, what is that? That is 0.1 repeating. That can be expressed as a fraction of integers, which is a rational number. And I can make that 1/9. That is exactly that. So this is rational. I'll star it for rational for all of our rational stuff. And you might be thinking, wait, how do you know that? Well, the algebraic explanation is a little complicated. But what I'd like to do is kind of bring this back. Well, how about we turn this into a decimal by division? I could show you that. So 1/9 is equal to 9 into 1, right? So 9 does not go into 1, 0 times. So I'll add a decimal and a 0, and 9 goes into 10 one time, which is 9. 10 minus 9 is 1. I'll add another 0, and 9 goes into 10 one time again, and you might notice what's happening here. I get this decimal 0.1, and this is going to keep on going, on and on and on, which is exactly our original decimal. So if I divide this and turn it into a decimal, I get that. So that means this, or this, is equal to that, because I can bring it back. So the next thing is this, 0.2 repeating. That is equal to 2/9. 0.3 repeating, that is 3/9, or it could be simplified to 1/3. 0.4 repeating is 4/9. Let's bring this down a little bit. Let's bring everything down a little bit. 0.5 repeating is 5/9. 0.6 repeating is 6/9, or 2/3. See, the point that I'm trying to make is all these repeating decimals, they are all rational. I'll star them because they are rational. They can all be expressed as a fraction of integers, which I'm doing at the end right here. See, blah, 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 blah. And I'm almost there. So 0.7 repeating is 7/9. And go ahead and plug them in the calculator. Do 7 divided by 9. You'll get 7 repeated. A little bit more here, because I'm getting to my favorite. So 0.8 repeating is 8/9, and 0.9 repeating is, oh man, what is that? Well, if you follow the pattern here, that should be 9/9, or 1. Isn't that weird? So all of these are rational because I'm ending up with fractions. This one troubles me a little bit, but there is a good explanation for this. How 0.9 repeating is equal to 1. So, I mean, if we look at this here, hold on. What I'm proposing is 0.9 repeating. What that means is 0.99999, all of these nines, forever. Forever. It just keeps on going. It never ends. That's equal to 1. Isn't that weird? I absolutely love it. Now my friend, Mr. T, he had a good idea too. He said, well, they have to be the same number because we cannot come up with a number in between them. And this probably follows some kind of theorem. He was mentioning, well, if you can't find a number, if you can't find a number between this and this, if there is no number in between them, then they have to be the same number. And yeah, you can't find a number between this and this because this goes on forever. If you think you're at the end, someone could add another 9 to it, and someone could add another 9 after that. So they are the same number, and so they are equal. There's no number in between. Anyway, back to our original problem here. This. So the fact that we can express this as a number over 9. So this is 151. Now, when I had 0.5 repeating, that is 5/9. If I have 0.45, so 2 numbers are under the bar, that would be 45 over 99. And the fact that I have 3 numbers under the bar here, that's going to be over 999. And the fact that I have a fraction here that is a fraction of integers, that is a rational number. So, must be a rational number. Done. Okay. Let's look at another. Okay. Now, I would say this one, I'm going to erase all this stuff here because we're looking at another problem. Now, this is not a fraction of integers. This is a fraction of decimals. So that's a problem. However, I could say that 0.4 over 0.8. 0.4, that is 4/10. And 0.8, that's 8/10. So, and then if I were to say 4/10 divided by 8/10, that's equal to 4/10 times, flip the second fraction, 10 over 8. These will cancel. I ended up with 4/8, which is equal to 1/2. In the end, wow, this whole thing turned out to be a fraction of integers, which is what a rational number is. So I'm thinking this is rational. Oh, the square root of 50. Well, I talked about square roots over here. Let me erase this here. I talked about square roots, and I mentioned that the square roots have to be perfect squares. So if I were to see the white ones, if you remember, the white ones are the perfect squares. So if I continue this list down here, what are the other perfect squares? The next ones are the square root of 36, that's 6, the square root of 49, which is 7, and the square root of 64 is 8. And the square root of 50, hold on, I'm going to do this. So the square root of 50 is in between those, and I put that in that color because that's irrational. Any square root in between the perfect squares are irrational. And so we bring this over here, and I will say that this is irrational. Hey, all right, this is looking good. 121. I know that the square root of 121, I happen to remember, the square root of 121 is equal to 11, which could be written as a fraction of integers. That means it has to be rational. All right. Pi right there. Pi just messes things up right there. That's automatically. Anything divided by or multiplied by pi is going to be irrational. And so, boom. Ha! Nailed it. All right. Well, I hope that this has been helpful for you. I leveled up. All right. Good luck on you trying it yourself. Thanks for watching.